Okay, welcome back everyone. So we will start from where we left in the previous week. So just giving you a quick recapitulation. So we were actually looking to solve for the velocity field inside a cylindrical pipe where the imposed pressure gradient was not a constant, which we actually thought of in the case of a Hagen possible flow, but now it is a constant multiplied by an oscillatory term, which basically says that okay, the pressure gradient changes its sign. You can interpret it as a oscillatory pressure gradient which changes in its sign periodically. Okay, so basically what we said is that dp dz, its magnitude, it was equal to an amplitude which is equal to g naught times this cos omega t term, which portrays the signature of the oscillatory behavior. Okay, so the objective was to derive solution for the velocity profile, and in doing so, in the process, we said that we are going to approach the governing equations non-dimensionally because we got a flavor of how the characteristic scales and the non-dimensional variables operate and their usefulness in solving and in evaluating analytical solutions to fluid flow problems. Okay, so what we did is we wrote down the simplified jet momentum equation in its dimensional form, and then of course written down the boundary conditions as well. So the boundary conditions were just the no slip at the wall interface, that is at the walls, and the fact that the velocity profile is bounded is the second boundary condition that we use. And so we begin by actually choosing the characteristic variable. For instance, in this problem we saw that there is a inherent or an imposed time scale that is present, which is equal to the inverse of the frequency. You can think of it like the time period of the, I mean, 2 pi by Tc is actually, going to be 2 pi by omega is actually going to be the time period, and inverse of the time period is the frequency, which is omega itself. Okay. So the meaning is the imposed time scale is nothing but, you know, the frequency at which, or in true sense, is the inverse of the frequency at which, the pressure gradient is imposed. And we also had a length scale for this problem. For instance, we saw that our length scale, we have chosen the length scale to be the radius of the pipe, and that's the only, plausible length scale that we had in this problem. And then what we said is that we actually balance the order of magnitude of the pressure gradient term with the viscous term. That is typically because we know that this is the term which actually dictates the fluid motion. Okay, the fluid is moving just because you are applying a pressure gradient whose amplitude is g naught with some oscillatory term. So this means if we are to seek, or if we are to find a characteristic velocity scale for this problem, I must balance the cause which is responsible for creating a velocity profile to the viscous term, which is kind of a messenger that this is. So it's like you are imposing a pressure gradient, and then we have this viscous term which says that okay, because of this imposed pressure gradient the fluid would basically move. Okay, that's one way of physically interpreting why are we actually, well, I mean, comparing the order of magnitude of this term along with this term. Okay, and then what we saw is that we got a scale for velocity which came out to be g naught times the length square divided by the dynamic viscosity, and we call this velocity as the characteristic velocity of the problem. Now remember, in this problem we have chosen the characteristic velocity to be of this form, typically because this is how I would I so typically because as I said that it's the pressure gradient which is responsible for creating a non-zero velocity field in this problem. Okay, now having said that, there can be multiple ways through which you can choose characteristic scales as we have discussed. Okay, now that being said, it is not always that you can naively choose a characteristic scale and get a correct interpretation or a correct representation of the dimensional counterpart. Okay, now that choice has to be wise, and that fact basically comes from the nature of the problem, and you must choose the characteristic scales in such a way that you capture the physics of the problem. Okay, that's the ultimate objective of choosing the correct characteristic scales in our problem. Because that being said, because I have we have seen multiple times that there can be more than one choice of the characteristic scales that we can encounter. Okay, So moving forward, so what we did is once we know the characteristic scales, we define the non-dimensional variable, which are just the dimensional variable divided by the characteristic variables. And then what we did is we substituted these non-dimensional variables into the dimensional governing equations to get, to transform the dimensional equation into the non-dimensional equation. And the final form of the non-dimensional equation that we saw is of this form, where we encountered a non-dimensional number, which we call it as alpha. In fact, we call it as alpha squared, where squared alpha is nothing but the free, it's sort of a Reynolds number, and you have that omega term that is coming, that is embedded in this Reynolds number, and that's why you call it as the frequency dependent Reynolds number. Okay. Now, of course, you can do a quick check and you can see that this term, the overall term, that is alpha square or root alpha, whatever you say, this overall term is non-dimensional in nature. Okay, which basically says that indeed equation 2 is non-dimensional, and any of the terms doesn't bear any dimension. They are just dimensionless. Okay. The second thing that we argued is that since these terms are non-dimensional, we can interpret these terms to be typically, in this case, to be typically of order 1 terms. That is something that you can interpret, but it is not. But remember, there is a word of caution that it is not necessarily the case that always you will encounter order 1 terms. Okay. In some instances, depending on which scale the problem is valid, or in which scale, or the different scales of the variable, you can have terms that may be order 1, or maybe some different scales, or maybe of some different order. Okay. But in this problem, you can say, because the cos t is generally going to be order 1, which means that this term has to be also order 1. And if you are equating an order 1 quantity with an order 1 quantity, that means that this alpha square del uj by del t is also going to be order 1. So this is something that you can do a quick check in order to see the magnitude of the different non-dimensional terms that you have. And lastly, or more importantly, I said that now we seek solution of this uj, which is now a function of r and t. And I said that the solution form that we will take is going to be of this form, where we assume that my uj, which is a function of r and t, is going to be some real part of function r times e power it. Okay, that's the form that we assume. And we will start from this point. And today what I will do is I'll give you a reason of so as to why I am assuming this form. Okay, so the question is, that should be naturally in your mind, that why did I choose this form of the solution, this form as a solution, as a possible solution for this uj. Okay, so there are multiple reasons for these answers. Okay, the first reason is that uh, maybe I should write reasons for assuming the above solution. Okay, so the first reason is that if you pay a close look or a closer look to this governing equation, you can see that the governing equation is linear. Okay, which means that my solution, you know since since this governing equation is linear, so one way, so this is just, it's not, I don't say this is the exact statement, but it's kind of a, it's kind of, how the solution solution will look like is going to be so basically is going to be described by this statement. So what I'm trying to say is that since this governing equation is linear, I can say that the solution, whatever solution of uj that I'm trying to figure out, that is also going to be linearly proportional to cos t. Now, if you calculate what is going to be, what basically is going to be linearly proportional to cos t, so you can see that real part of e power it is nothing but cos t. Okay, so in a way, I'm just, so if you just, for a time being, if you just neglect this u hat of r term, the real part of this e power it is just going to be cos t. So since the governing equation is linear, I can roughly say that my solution is going to be linearly proportional to e power cos t, and that's one of the reasons which motivates me to take the form of the solution in this manner. So the only thing that we now need to evaluate is this u hat of r, because that's the unknown that we don't know, that how is u hat is basically going to vary along the radial distance. But at least I know that the temporal term is also going to behave in the similar way as cos t behaves. Okay, and that is something that I can say because my governing equations are linear. Okay, so the first reason is that uh, since the governing equations are linear, so the solution can be interpreted to be linearly proportional to, maybe I'll write real part of e power I t. Okay. Okay, that's uh okay, that's one of the reason. And the second reason that you can, so the second reason is more physical. I mean, it's kind of a more physical reason. So what you can think is that, okay, I'll go to the schematic. So what you can think is that, since there is a applied pressure gradient, okay, with some frequency omega, you know that because this pressure gradient is kind of oscillating back and forth, I know that my fluid is also going to oscillate back and forth. Okay. For instance, if I draw the velocity profile, at one time instant the velocity profile will be like this, at the other time instant the velocity profile can be like this. Okay. So what I'm trying to say is that, since it's the pressure gradient that dictates the nature of the flow field, and I know that the pressure gradient is oscillatory in nature, this means that my fluid is also going to oscillate back and forth, at least with some phase change. Okay. So in other words, what I'm trying to say is that in this problem, although it is a transient problem, we'll basically trying to look for time periodic solutions. Okay. That's the second set the second reason. Okay, I hope you are clear. It just boils down to the nature of the pressure gradient that we are just applying. Okay, because the nature of the pressure gradient is oscillatory in nature, I know that my fluid will also oscillate with time, with some phase change that I know because of viscosity. But at least I know that the solutions that the velocity field will exhibit will be time periodic in nature. Okay, so the second reason is we seek time periodic solution. uh, and maybe I can write that the nature of the applied pressure gradient uh, will also, or maybe will result in the flow field to oscillate back and forth with some phase lag. Okay, so this term phase lag actually is important, and you will realize once we write the solution. Maybe you have also encountered this when you studied the Stokes second problem. This means that the fluid will also not oscillate with omega, rather because of the fact that the fluid is viscous, it will oscillate with some other frequency, but there you can basically relate that frequency with some lag to the otherwise imposed frequency of the pressure gradient. Okay, that typically is meant by this term phase lag. It will be clear when we look into the solution of UZ of R comma D that we will see. So because, see, this is important, because since we are now looking time periodic solution, what we will see is, in this solution we will not actually treat time as a variable and impose an initial condition on t, but rather treat time as some kind of a parameter, because we know that our solutions are anyway going to be anyway going to be linearly proportional to real part of e power it. So it's like, in this problem we are going to treat time as a parameter, rather than treating as a separate independent variable and imposing an initial condition on this problem. Okay, so the nature of the solution mandates, or hints us that we actually don't require initial condition on the variable on uj at t equal to 0, because we are looking for time periodic solutions, or in plain sense, we anyway know that my solution is going to oscillate, the velocity field is anyway going to oscillate with time. Okay, so this statement also hints that, we don't require an initial condition in this analysis. Okay, I believe so far you are with me on this. Okay, so what we see is we try to find out the reason why are we choosing the solution form of this nature. Okay, and these are the plausible reasons that you can state or that you can use to justify the solution form that you have assumed in order to evaluate the velocity field UZ. Okay, so now I hope this is clear. So now what we'll do is, once we know the solution form, I believe you now know the steps. We just need to substitute 3 in equation 2. Okay, that's all that we need to do. So what I'll do is I'll substitute this form in equation 2 and evaluate the terms part by part. Okay. Okay, that's it. So now that's what we'll do now. So substitute 3 in 2. Okay. So let's calculate this part by part. Okay. So first in the left hand side we have the term alpha square del u z by del t. So we have this term alpha square del u z by del t, and we can write this as del t of real part of u hat of r e power I t. But I know that this is just a function of r. That means I can then write this as I alpha square, because so we just have a derivative with time. This is just a function of r, which means I can then write it as I alpha squared times real part of u hat of r e power I t. Okay, that's going to be the left hand side. That is so maybe what I'll do is I'll call this as term A. I'll call this as term A, I'll call this as term B, and I'll call this as term C. Okay, and I'll separately substitute the solution UZ of R comma T as this form into these terms A, B, and C. That's exactly what we are doing here. Okay. All right. So let's now look term B. So this is term A. This is term A. Okay. Let's look at term B. So the term B is just cos T. So this is simple because I can write cos t as just real part of e power it. Okay, so this is from the Euler's formula that I hope you understand, that e power I theta is basically equal to cos theta plus I sin theta. That's what that's what is, and then the real part of this e power I theta is going to be this cos theta. That's exactly what you're writing here. Okay. All right. So that is your term B. And let's now see the term C. So in the term C, what do we have? So we have uh, in the third term, or in the C term, we have del 1 by r, del r of r times del uz by del r. I think this is the term that we have. Okay. And we will substitute the fact that uz is equal to this term, that is real part of, so we'll just substitute uz to be this. So then what will we get? So we will get something like this. So you can do the substitution and we'll just get, this is some real part of e power I t 1 by r del r of r times del u hat, maybe, yeah, so it's del u hat by del r. Okay, but I know that u hat is just a function of r only. Okay, so then I can replace this del with the d operator, which means this becomes real part of e power I t 1 upon r tdr of r times du hat by dr. Okay, all right, that's it. So this becomes your term C. Okay, so then the complete equation is just, stitching all these terms together. So the complete equation is going to be, so in the left hand side, we have term A, which is just I alpha squared, real part of u hat of r, e power I t, and then I have real part of e power I t, okay, and then I have the c term, which is, maybe I'll write it here, it's real part of e power I t 1 by r ddr of r times du hat by dr. Okay, that's my term. That's the complete equation that we get after we do the substitution of the form of solution that we are seeking for using. Okay, so now we'll do one thing. See, we know that whatever v, so see, ultimately we are interested in finding out this u hat of r. That's all that we are that we are trying to evaluate, right? So I hope you realize that this is the prime variable that we are trying to evaluate. Okay, this is the, what to say, independent, or maybe, oh, sorry, not in, so maybe I'll write it that this is the variable that we see. Okay, which means what I can do is, in this equation I can discard the real part and solve for u hat of r, and then once the solution comes, I will tell that the solution is going to be the real part of whatever the u hat of r that we will get. Okay, in other words, what we'll do is we'll discard this real part, and maybe we'll get some u hat of r, let's say, as a plus ib. Okay, something like this, and then I will tell that the solution is going to be this real part of u hat of r times e power it. That's all that I will say once I know what is u hat, what is basically u hat of r. So I hope this is clear that we are not just merely cancelling this real part, but we are saying that we will solve for u hat, and then once we get the solution for u hat, I will just take the real part of that u hat times e power it. That is going to be the desired solution that we are that we are trying to evaluate. So then this equation can be rewritten as I alpha squared u hat of r e power it, and this is e power it, okay, plus e power it 1 by r ddr of r times du hat by dr. Okay. All right, so now we can say that since e power it can't be equal to 0, because if that is 0, we'll end up getting a trivial solution, which means that I can cancel this e power it, and then I will end up getting a ODE, which is of this from I alpha square u hat, and this is just going to be equal to 1 plus 1 by r ddr of r times du hat by dr. Okay. That's it. That's the ODE. So we'll do some little bit of manipulation. What I will do is I will apply product rule here and expand this term. So if I expand this term is just going to be equal to 1 upon r du hat by dr plus r times d2 u hat by dr2. This is going to be this term, and then I can bring this 1 by r, and then this term will just simplify to, it's just some simplification that we are doing. So it is just going to be I alpha square u hat plus 1 plus 1 by r du hat by dr plus d2 u hat by dr2. Okay, and maybe if I just bring all the terms to the other side and the one term to the opposite end, I will just get d2 u hat by dr2 plus 1 upon r du hat by dr plus, or maybe there will be a minus, yeah, so minus IR. So what I'm doing is I'm just taking this one here and I'm just taking this one there. That's what I'm doing. Okay. This is minus I alpha squared u hat, and then this is going to be equal to minus 1. That's it. So essentially what we have done is, I hope you have realized that we have converted the PD by assuming the form to be of some real part of u hat of r times e power it. We have essentially converted the PD into an ODE. Okay, and we know how to solve ODEs. Okay, so that's the ODE that we get after simplification. So oops. Okay, so I hope you realize that this is, first of all, this is an ODE which is second order. Okay, it is non-homogeneous because we have this minus 1 term. So this is non-homogeneous. Okay, and also there is a little bit of complexity in this ODE, is that the variables or sorry, the coefficients of the terms u hat or the derivatives of u hat, the coefficients are not constants but they are variables basically. Okay, so this is a ODE with variable coefficients. Okay, so we have the coefficients to be variables. Okay, so that's it. So if we have an ODE which is non-homogeneous, first of all we know that the solution, that is u hat of r, is going to be a complementary function. We'll call it as uc hat of r plus the particular integral up hat of r. Okay, that's the standard way how we solve ODEs which are non-homogeneous. Okay, so they're so this is how we solve basically second order ODE which are non-homogeneous. We tell that we will tell that the solution is going to comprise of a complementary function which will satisfy the homogeneous part, which is basically this is what UC satisfies, and the particular integral satisfies the entire ODE. Okay, so that's basically is the solution that we seek for. Okay, maybe I'll number the equations. So okay, so this is 3, this is 4, and maybe this is 5. Okay, now luckily in equation 4, you can basically have a look at equation 4, and just by inspection you can find out the particular integral. So what if I say that my particular integral, that is up of r, is going to be equal to 1 by I alpha squared. Okay, that is, I just take this term, I just divide it. So I just look into these terms and I say that my particular integral, which is up, is just going to be 1 by I alpha squared. See, this is true because you know that up is going to satisfy the entire ODE. So take this up and just substitute it here. You will simply get that this is true. See, this is just going to be 0. This is also going to be 0, and I know that this is minus 1 by I alpha squared, which means this will just get cancelled. Okay, and I have minus 1 equal to minus 1, and indeed the equation is satisfied. Okay, so luckily I know that just by inspection I can calculate the particular integral in this problem. Okay, so this is something that I get uh, by inspection. Okay, but maybe in some complex problem where you cannot, where inspection doesn't help, you basically need to look into more standard approaches for calculating particular integrals. uh, so for constant coefficients, ODEs with constant coefficient, we have something known as method of variation of parameters. So you can use method of variation of parameters to calculate the particular integral for constant coefficients. Okay, but anyways, in this problem, luckily we know that just by inspection, I know that my particular integral is just going to be 1 by I alpha squared. And if you ask me how, just take this and substitute it here. You will see that your ODE is solved. And if your ODE is solved, if this is the solution, you can prove that this is precisely the unique solution. Okay, that is something that the math says. Okay, that's it. So I have the particular integral. All I now need to calculate is the complementary function. Okay, so calculation of UC hat of R. Okay, and I know that UC hat of R satisfies the homogeneous part, which means my UC hat satisfies. So UC hat satisfies the homogeneous part of equation what 4, that is d2 uc by dr2, okay, plus 1 upon r duc hat by dr minus I alpha square uc hat is equal to 0. Okay, so what I will do is I will multiply the entire equation by r squared. So I will get r squared times d2 uc by dr2 plus r times duc hat by dr minus I alpha squared r squared times uc hat is equal to 0. Okay. All right. So this is the equation that UC satisfied, or in other words, we now need to evaluate what is UC. That's all that we require. Okay. For that, what I will do is I'll do a quick change of variable now, due to a certain reason. The reason will be clarified to you very shortly. So what I'll do is I'll do a change of variable. Okay. So I'll do a change of variable. So I'll define something known as r tilde as square root of, or maybe okay, so I'll define as square root of I alpha r. Okay, so basically what I'm doing is I'm just considering this term as r tilde squared. That's what I'm doing. Okay, so this is the change of variable that I'm using in this equation, and why we are doing this will be very clear in couple of minutes. Okay, so if we are doing this change of variable, then I must also apply this change of variable in this term and this term. So let's first of all apply this into the derivatives. So then duc hat by dr is going to be equal to duc hat by dr tilde times dr tilde by dr. That's simple chain rule. And then I know that dr tilde, so from this equation, I know that dr tilde by dr is just going to be alpha r root over I. Okay, so this is just going to be equal to alpha r root I. Sorry, r is not going to be there. I'm very sorry, because I'm taking the derivatives. So that's it. So what I'm doing is I'm just taking this. Okay, dr tilde by dr is just going to be equal to alpha times root over I. That's what I'm doing. Okay, so that's precisely this term. So it is going to be alpha times root I times duc hat by dr tilde. And similarly, you can show that your d2 uc hat by dr2 is going to be equal to alpha square I d uc hat by dr tilde. All you need to do is you just need to differentiate this with respect to dr once again and then apply the subsequent chain rule. Okay, so that's it. Let's now just substitute these change in variables into this equation. So then what we'll get? So r square is going to be r tilde square divided by this term. That's going to be r squared. So then I will have this as r tilde squared by I alpha squared. This is going to be, so this is going to be r squared, and then d2 uc by dr2 is going to be this term. So this is going to be alpha square I times dcu hat by dr tilde. Okay, and then I have, so r is going to be r tilde by alpha root I, and then this uc hat by dr is going to be this term. This is just some algebra, so you don't need to be really, there's nothing really uh, physics here, just algebra. Okay, this is just going to be your the derivative, and then I have this term which is just going to be equal to minus of r tilde square uc hat is equal to 0. That's it. So in simple terms, what I'm doing is I'm trying to transform this ODE into an equation in UC with a different variable, which is r tilde. And for that, I'm just doing this transformation and evaluating these derivatives. That's all that I'm doing. Okay. So then you can see that this and this cancels, this term and this term cancels, and I just have r tilde squared duc hat by dr tilde plus r tilde times duc hat by dr tilde. This is squared. Okay, I think I made a mistake. Yeah, this is squared. Okay, I'm taking the derivative, so this is going to be squared. Exactly. Okay, and then I have r tilde times this, and then I have this term r tilde squared times uc hat is equal to 0. Okay, so this is the equation that governs uc hat in terms of the change variable r tilde. Maybe I will box this, and maybe I shall name this equation as what. So this is maybe 6, this may be 7, and this may be 8. Okay. All right, so there is a famous equation which is of this form. Okay, x squared times d2u x2 plus x times du by dx minus x squared minus mu squared times u is equal to 0. So this equation has got a name. This is known as the modified Bessel's equation. Okay, had this been plus, this equation would have been just the Bessel's equation, but this equation with a minus sign, this is known as the modified Bessel's equation. Okay, and this equation is so famous that people have eventually calculated that the solution to this equation, which is u as a function of x, are going to be the modified Bessel functions, which is just some constant time j nu of x plus some b times y mu of x, where these j's and y's, these are known as the modified Bessel function. These are known as the modified Bessel function of first and second kind. And this nu is known as the order of the Bessel's equation. Okay, so this is nu. So this nu is the order of the Bessel equation, or maybe I should say modified Bessel's equation, because this is modified Bessel's equation. Okay, so what I'm trying to say is that if you encounter a equation of this form, okay, where nu is just some parameter, then we know that the solution is going to be consisting of the Bessel functions, or and in this case these are nothing but the modified Bessel functions of the first and second kind. And if you have this parameter as nu, then the order of these Bessel functions are also going to be nu, basically. Okay, so you can tell that the solutions are going to be linear combination of the modified Bessel's equations, or sorry, modified Bessel functions of order nu. Okay, if you basically have an equation of this form. So now can you carefully observe this equation and tell me and tell some similarities with this equation and this equation. So very nicely you can see that you exactly get this equation. So from this equation you exactly get this equation if your nu is basically equal to 0, which means this equation 8 is a Bessel's equation of order 0. Okay, where nu is typically equal to 0. Okay, so equation 8, so by comparison with the standard modified Bessel's equation, equation 8 is a modified Bessel's equation of order 0, which then means that my solution, which is u hat c of r tilde, they are going to be just the modified Bessel functions of the first and second kind. So my solution is going to be, let's say, some c1 times of j0 of r tilde plus c2 times of y0 of r tilde, because I know that nu is typically equal to 0, because I don't, so precisely from this term I can interpret that this is going to be the solution with order 0. Okay, Okay, that's it. That means we just know the solutions, right? Because we know that since this is kind of a, since this equation is a modified Bessel's equation, the solutions are going to be a linear superposition of the Bessel's equation or the Bessel function of the modified Bessel function of order 0 of first kind and the modified Bessel function of order 0 of second kind. Okay. And then since we see, remember we this was in terms of r tilde, but the actual variable was r. So we again, retransform this r tilde back into r. So where we know that my r is going to be just r tilde divided by this quantity. So then this uc hat of r by alpha root I, okay, which you can call it as just uc hat as a function of r, because a function of this quantity is equivalently a simple function of r, because this is just a constant, okay. And then you can call it as c1 times j0 of, okay, hold on, did I do some mistake here? Okay, r tilde is this, it's 1 second, r tilde is this, yeah, exactly. So i I think this is not going to be divide, because see what was r tilde? R tilde was r times alpha root I, and that's what we are going to substitute here, which means that my uc hat of r is going to be some c1 times j0 of r alpha root I plus c2 times y0 of r alpha root I. Yeah, it's not going to divide, it's going to multiply, because that's how we defined r tilde. Okay, that's what so what we are doing is we are just replacing r tilde with r using this relation. That's all that we are doing. Okay, so okay, so that's it. That's the solution of your complementary function. Okay, where the c1 and c2, these are some arbitrary constants, and as I said, j0 and y0 are the modified Bessel function of order 0. Okay, now in this, what we'll do is we'll apply one of the boundary condition. Remember, we call, so there was a boundary condition which was the boundedness boundary condition. So we said that, so in the boundary condition 2, that is the second boundary condition, we said that my magnitude of uz is bounded. Okay, that means that whatever the solution of uz is, okay, it cannot basically reach to infinity or minus infinity. Okay, but we know that, so if you plot the modified Bessel's equation of second kind, and this is important, okay, if you plot the modified Bessel's equation of second kind, this this modified Bessel function, I'm sorry, if you plot the modified Bessel function of second kind, then at r equal to 0, this term basically blows up, which means in order to have uz as bounded, I must have c2 to be equal to 0. Okay, this is necessary for uz to be bounded. And the reason is, since y0 of 0, that is y0 at r equal to 0, basically blows out or blows up. So in since I know that this term basically blows up, the only way I can have this term to be bounded is that I need to choose C2 to be equal to 0. Okay. So therefore, your complementary function, therefore, UC hat of R is going to be just some C1 times the modified Bessel's function of the first kind of order 0, of course, times R alpha root I. Okay, so then the complete solution, you remember the complete solution is u hat of r is equal to your uc hat of r plus your particular integral up hat of r, and I know that my uc hat of r is j1, sorry, c1 j0 r alpha root I plus the particular integral. If you remember, it is just going to be, so what was the particular integral? So this was your particular integral, right? So it is 1 by I alpha squared. Okay, so this is going to be 1 by I alpha squared. Okay, so that is going to be your u hat of r. Okay, so remember, we also need to evaluate, maybe I should name this equation. So this is 8, this maybe is 9, this is 10, and this is 11. So remember, C1 is yet to be evaluated, okay? And for which we will apply the first boundary condition. So the first boundary condition, says that my UZ at R equal to capital R for all time is 0. And that is typically your no-slip boundary condition. Which means I know that UZ is real part of U hat of R times e power it to be equal to 0. And for this to be possible, the only option is that U hat of R is equal to 0. Okay. And this is true at R equal to capital R. Okay. So if we use this condition in equation 11, then what I get? So I get 0 to be equal to C1 times J0. Now I'm evaluating R at capital R. So this becomes R times what? Alpha root I, okay, plus 1 by I alpha squared, which then gives me, C1 as, okay, so what is C1? So C1 is going to be minus 1 by I alpha squared by J0 of R alpha root I, okay? Or maybe I'll write this C1 as minus 1 by I alpha squared J0 of R alpha root I. That's it. That's my C1. Okay. So we have evaluated all the constants in this equation. I mean in the solution. So then your complete solution is going to be this. The complete solution for U hat is going to be this, which means it's so your U hat of R is going to be what? So it is going to be C1 times J0 of this, and I know that C1 is basically this. So C1 is equal to minus 1 I alpha squared J0 of R alpha root I. This is going to be my C1, and then this is multiplied with J0 times of this quantity, okay? Okay, sorry, I think, yeah, sorry, I think I need to look here. Okay, so this is J0 of this quantity, which is, so I'll just write it here. J0 of R alpha root I, okay? And then I have the particular integral as well, which is what? Which is just this quantity, which is 1 by I alpha squared. So that's it, plus 1 by I alpha squared, okay? So, so maybe if I write it, so, but remember, U hat of R is, so remember, U hat is not what we are seeking, we are actually seeking UZ, okay? So we also need to calculate UZ, but U hat of R is going to be 1 by I alpha squared, okay? So if you take I alpha squared common, you will get 1 minus J0 of R alpha root I by J0 of capital R alpha root I, and this is going to be your U hat of R, okay? Maybe I'll name these equations. This is equation 13 and this is equation 14. But remember, my actual variable was UZ of RT and RT, right? And we know that my UZ of R comma T is going to be equal to real part of U hat of R e power it, and I know that U hat of R is this. So the complete solution is going to be real part of 1 by I alpha squared 1 minus J0 of R alpha root I by J0 of R alpha root I, okay, times e power it. That's it. So you compute this, take the real part, and that is going to be your solution for the velocity field, okay? That's typically your velocity field UZ, which of course is a function of R and T, as you can see, okay? So that's the complete velocity field. Okay, that's it. That's your solution then. That's the solution of UZ that we are actually, trying to figure out. Okay. So yeah, I understand the algebra is little bit involved here, but you need to do algebra if you are into fluid mechanics. That's the if you are into postgraduate fluid mechanics. That's what everyone says, and that's the harsh truth of it. Okay. So so I understand the algebra is complicated, but yeah, it's fun basically because you can see since you can write analytical solutions, you actually can develop a lot of insights into these problems. Okay, like into the steps, the nature of the solutions that we saw. You can actually do that because you are able to write analytical solutions to the velocity field. Okay, but remember, see, is this is basically a non-dimensional equation. You can, so what I will ask you to now do is derive the dimensional equation for this and match it with the one that you have derived in the lecture series. Okay, you should precisely get the exact equation that we have done, that you have derived when you solve this problem dimensionally in while you are watching the lecture series. Okay, so so the job that you need to do is this is a non-dimensional equation. You can see because these are non-dimensional variables, r, alpha, and all those quantity. What we need to do is use now the characteristic variables, okay, and transform this non-dimensional solution into the dimensional solution, and then compare it with the one that we have derived when you solve the problem dimensionally, and you should exactly get the same expression for uz, albeit now you are getting the dimensional form of the non-dimensional counterpart. Okay. All right, so this finishes the solution to this oscillatory pressure gradient in a cylindrical pipe. Okay, we will now move ahead to a different kind of solution, which is the agenda for this week, which is steady 2D rectilinear flows. And I believe we have gone through the solution of calculating, calculating solutions to something known as methods. So basically, what we'll do is we'll try to calculate solution to or figure out solutions to Laplace equations by using something known as method of separation of variable. And the one that we just now saw, that the solution from that we just now derived, this is one kind of a method of separation of variable where we a priori know that the function of time is going to be oscillatory in nature. Okay, so or we know that the solution is going to be time periodic. So this is one form of separation of variable. But now in this discussion, that is trying to solve 2D rectilinear flows, okay, we use the most general procedure for solving problems. For instance, we'll solve a Laplace equation here, as we will see very shortly, and we will use the most general form of the procedure of separation of variable. Okay, in this problem. So this is the agenda for the next problem that we are going to solve. But here I'll take a couple of so maybe I'll stop here for a couple of minutes, and this is the problem that we will solve. You have solved a very similar problem in the lecture series. And what we will do is, again, we'll do the same exercise. We will start off from the dimensional version of the equations, transform the dimensional form into non-dimensional form, and try to look into the solution of the non-dimensional form. And your job would be just the same. You need to transform the solution of the non. So I will derive the solution of the non-dimensional form, but you need to again transform the non-dimensional version into the dimensional form and match the solution with the one that you got in the lecture series, and your solutions are exactly going in principle your solutions should exactly be the same, irrespective of what choices of scales that you make in deriving the non-dimensional counterpart. Okay, but before that, I'll stop here for a couple of minutes. You can read the question. So it's a similar question. We are trying to calculate the velocity field that is flowing through a rectangular duct, considering that it's a fully developed flow. Okay, based on this information and based on the fact that the fluid is Newtonian and things like that, our job is to calculate the velocity field. Okay, that's all that we'll do. But I'll stop here for a couple of minutes. I'll come in maybe 2 minutes. I'll fill my mug with some water and I'll be back in 2 minutes. Till then, you can read this question and try to devise a solution procedure. Okay, let's get started. So as I said, we will now, go ahead and solve something known as 2D rectilinear flows. Uh, and the reason, as I said, why it is called 2D is that because I instead of having a plate which is infinitely having a large width, I will now say that okay, the length, I mean the breadth and the width of the plate is finite, and the fluid is kind of flowing in a plane which is perpendicular to the cross section of the plate. Okay. Given this scenario, our job is to calculate the velocity profile, that is W, which is the z component of velocity profile, as a function of x and y. So this is going to be a function of x and y because we are assuming that the flow is fully developed, that which means that my variables are not going to be functions of j. Okay. And just to say that the flow is actuated now by applying a constant pressure gradient instead, so we'll not consider any oscillatory pressure gradient here, but just for the sake of simplicity we'll say that the flow is being actuated in the z direction by applying a constant pressure gradient whose magnitude is just equal to g. Okay. And one more thing, so we will consider the height, and I mean, okay, we'll consider the width and the height to be of the same dimension, meaning that we'll consider a to be equal to b. So in principle the cross section is square in nature, and we are trying to look into the flow through a square duct. Okay. That's a so you can keep your a's and b's to be generic, but here, just for some simplicity, we are considering a to be equal to b, that is this cross section is indeed square in nature. Okay. So based on this and considering the fact that it's a fully developed flow, our objective is to evaluate the steady state velocity profile. That's we'll try to do. That is what we'll try to do. Okay. So I'll skip the preliminary steps. You know what basically needs to be done. Write down the equation, write down the entire z momentum equation, because you know that the flow is basically actuated by a pressure gradient along the z direction. So you need to write down the entire z momentum equation and just invoke the assumption. That's it. For instance, the flow is steady. Okay, it's fully developed, and it's a 1D flow. I mean that so even if the variable is varying along x and y, I know that the flow is unidirectional in nature. That is I just have a z component of velocity, invoke all these assumptions, and you will see that the simplified z momentum equation, the simplified z momentum equation is going to be something like this. So the left hand side is just going to be 0 because we don't have any transient term, and the other terms, that is u grad u, they will all go out to oblivion if you invoke the assumptions. Okay, this is for you to try and check it out. And then I have the pressure gradient by that, but I know that my minus dp dz is going to be g plus mu times del square w prime. Remember, my primed variables are dimensional variables. That is something that we have been following since the previous problem. So this is a dimensional equation, as you can see, and this is going to be x prime squared plus del 2w prime by del y prime squared. I'm not going to write the next term, which is del 2w prime by del z squared, because I know that this is 0 by the condition of fully developed flow. Okay, and then this is it. Okay, so that's your simplified dimensional z momentum equation. And as I said, we'll do the same exercise. We will first of all, okay, let's first of all write down the boundary conditions as well. So the boundary conditions are, see, boundary conditions are rather simple, right? Because I know that here, and here, in basically along the four boundaries, I know that on account of the no slip boundary condition, the flow field is going to be equal to 0. Okay, which means that my w for all x at y equal to plus and minus of p is equal to 0, and my w at x prime equal to plus and minus of a, and for all y this is going to be equal to 0. Okay, these are my boundary conditions, and I know that my a is just equal to b because it's just a square term. Okay. All right, that's it. So we are that's the thing. We require to solve equation 1 subject to these two boundary conditions, these four boundary conditions to be precise, because I'm writing this at plus minus b and plus minus a. Okay. All right. So I believe now you know the steps. So what? So the step 1 is the characteristic variables. So what we will do is we have, a characteristic length scale which is either B or A, because I know that A is equal to B. So you can choose it to be either B or A. That's the same thing. Okay. And that's it. That's all that I have. So I'll say that my characteristic velocity is UC, and I'll try to find it out by matching the order of magnitude of this term and this term. So if you do that, you can see that your G should scale as mu UC by LC squared. Okay. So just compare. So just, take the order of magnitude of this term and take the order of magnitude of this term as we had been doing before, and you will see that your G should be equal to mu UC by LC square, which means that the scale for velocity UC is going to be equal to G LC squared by mu. So that's my velocity scale. This is the same scale that we got in the previous problem as well, where G, remember, G was the amplitude of the oscillatory pressure gradient. Here we don't have the oscillatory term, rather the pressure gradient is just constant. Okay. So this is the velocity scale. Okay, that's it. So then I can now define a non-dimensional W, which is a dimensional W by the characteristic velocity. I can define a non-dimensional X as my dimensional X by LC, and I can define a non-dimensional Y as my dimensional Y by LC. That's it. So these are my non-dimensional variables. I am, going a little fast in these steps because we had been doing this repeatedly in the previous problem as well. Okay, that's it. So the next step is, so this is the step 1. So the step 2 is the deriving the non-dimensional equation. So the non-dimensional equation. Okay. So let's try to derive the non-dimensional equation. So I have 0 in the left hand side and I have G plus mu. This term is just going to give you UC by LC squared, and then I'm just going to have del squared W by del X squared plus del squared W by del Y squared. I'm just doing, so what I'm doing is I'm just writing W prime as W times UC. That's all that I'm doing, and I'm also writing X prime and Y prime as X times LC and Y times LC. That's all, that I'm doing. And from here you are basically just getting this term. That's it. Okay. But I know that I have already derived that my UC is equal to GLC squared by mu. Okay, that's UC. That means I can just substitute it here, and then I'll get 0 equal to G plus mu by LC squared, and I know that UC is equal to GLC squared by mu, and then I have del squared W by del X squared plus del squared W by del Y squared. Okay. And then you can do this cancellation. So LC squared and LC squared will get cancelled, mu and mu will get cancelled, and G you can just divide by G and G will just get cancelled, which means the equation just simplifies to del square W by del X squared plus del square W by del Y square equal to -1, because I will have a 1 here, and I take the 1 to the other side of the equal sign. So this equation can be equivalently written as del squared of W equal to -1, okay, where this del square is known as the Laplacian operator, and in Cartesian 2D form, this Laplacian operator, as you can interpret, this takes the following from del 2 by del x2 plus del 2 by del I2. Okay. And the entire equation, this del square W by del square W equal to -1, this equation has got a special name. This is known as a Poisson equation. Okay. So that's it. Our job is to solve this Poisson equation subject to the boundary conditions. That's all that we need to do. Okay. So then let's also write down the boundary conditions in non-dimensional form. So I know that. So boundary conditions in non-dimensional form. Okay. So I know that my u prime, that is my dimensional u prime at x equal to plus and minus of a for all y is equal to 0. So then so I believe you can interpret that in non-dimensional form it is going to be u at x. So this is prime, and then this is x equal to plus and minus of 1 is basically equal to 0. Okay, because I can always write u prime. So what I'm doing is I'm writing u prime as the non-dimensional w times uc, and I'm writing x prime as my non-dimensional x times lc. And I know that when x prime basically goes from minus a to a, or equivalently minus b to b, because your a is equal to b, I know that my x will basically go from minus 1 to 1, typically because x is just going to be equal to x prime by lc. Okay, that's what I have been using. So that's precisely what I have been using, or maybe I'll make it like this. Okay, that's precisely what I have been using here, basically. Okay, so this is going to be your boundary condition in the non-dimensional form. Maybe I should name the equations. Okay, maybe I'll name this as 3. I'll name this as 3a. Okay, and similarly the other boundary condition will just give you that u for all x at y equal to plus and minus of 1 is going to be equal to 0. Okay, and I will name this equation as 3b. Okay, that's it. So what we need to do is we now need to solve equation 3, okay, which is just the Poisson equation, which is del square of omega, or sorry, w equal to 1 equal to minus 1, subject to these two boundary conditions. Okay, that's it. That's all that we need to do in order to evaluate the velocity profile. Okay, maybe I'll stop here for a couple of minutes. Please let me know if there are any doubts here. Sorry for that. Yeah. All right. Maybe I'll write down the summary. So we need to solve del square w equal to minus 1, subject to the fact that w at x equal to plus and minus of 1 for all y is equal to 0, and w for all x and y equal to plus and minus of 1, this is equal to 0. Okay, this is all that we need to solve for. Okay, where you know that this del square operator is just del 2 by c, just a shorthand notation of this partial derivative space, which, as I said, is called the Laplacian operator. Okay, so now here is the thing that you need to understand. See, had this equation been just del square w equal to 0, which is known as the Laplace equation, we would have just taken w to be of the form some x of x times some capital Y of y, which is the classic separation of variable technique. But now, since we have a non-homogeneous part here, we cannot directly incorporate separation of variable because the equation is not homogeneous here. Okay, so for this what we will do is we will anyway try to use separation of variable just by doing a slight modification, or by just taking a form of solution of a particular form. Okay, so what we'll say is that we'll assume w, which is a function of x and y, as some w1 of x, which is just a function of x, plus some w2 of x and y. Okay, and this I can do because, as I said, the governing equation is linear. I can take two different so basically I can add the simplistic forms and superimpose them to get the entire variable. Basically that's one way of interpreting it. Okay, and this I can do. See, remember this breakdown, this I can do because I know that my governing equations is so the governing equations are linear in nature. Okay, so then what I'll do is then w1 of x satisfies, since w1 is just a function of x, this will satisfy d2w1 by dx2 equal to minus 1, subject to the fact that w1 at x equal to plus and minus 1 is equal to 0, because I know that I have So I have decomposed this solution in such a way that this non-homogeneous part I have included them into a separate solution which is just a function of x. Okay, and doing so, I know that since w1 is just a function of x, I just now need to solve the ODE, okay, which is just of this form, which is very simple. We know the solution of this particular ODE. Okay, in fact, the solution is just going to give you the solution of a plane possible flow in non-dimensional form. And then what I will say is that since w1 satisfied this, I know that equivalently w2, which is a function of x and y, will satisfy. So what will then w2 satisfy? It is just going to satisfy this del square w2 by del x2 plus del square w2 by del y2 to be equal to 0. Okay, so what I have done is just by just by applying the principle of superposition, I have transformed the Poisson equation into a Laplace equation where the non-homogeneous part can be solved by just merely solving an ODE. Okay, and all the other contributions which will take care of the variable which depends both on x and y is clubbed into the Laplace equation. Okay, and then w2 satisfies what? So so we will see what w2 satisfied, because see, if I see, you can easily do this, because if you add this and this, you get back the original equation. Okay, and this you can do again, I say, because your governing equation is linear in nature. Okay, so just to see that if your equation is correct or not, just add this and this, you simply get the old equation, because you will just have d2w1 by dx2 plus del 2 w2 by del x2, plus I can write this as del 2 w2 plus w1, but I know that w1 is just a function of x times del y2. Okay, so this equation, and then we'll have a minus 1 here, and so this equation will simply boils down to your del square w is equal to minus 1. Okay, so that is something that you can verify at your end. Okay, so then we now need to evaluate, but before that, let's name these equations. Maybe I will call this as 4 with the boundary condition 4a, and I'll call this as 5. But now let's figure out what will be the boundary condition for w2. See, I know that my that w at x equal to plus and minus of 1, okay, for all y is going to be equal to 0 for no slip, and I have decomposed w as some w1 at x equal to plus and minus of 1, okay, plus w2 at x equal to plus and minus of what? 1 of all y is equal to 0, which means my boundary condition for w2 is going to be w2 at x equal to plus and minus of 1, okay, for all y is going to be minus of w1 at x equal to plus and minus of 1. That's it. Okay. Okay. I think I made a mistake in this boundary condition. Okay. Okay, sorry. I think I made a mistake here. Okay. Okay. See why I have made a mistake is because here I know that this function is just going to be some function of y, but this is just a function of x. So maybe it's the other way around, that is more appropriate here. Okay, so what I should have written here is, okay, so let's okay, so let's okay, let's write down this boundary condition as well. So it says that w, so the original boundary condition is w at x equal to plus and minus of y, plus and minus of 1 for all y is going to be 0. But I know that this is equivalently going to be w2 at x equal to plus and minus of 1 for all y to be equal to 0, because I know that w1 is just a function of x only. Okay, which means I cannot have w1 to be a function of y, which means that the first boundary condition is just going to be equal to this w2 at x equal to plus and minus of y to be equal to 0. Okay, maybe I will write this as 5a. The second boundary condition is going to be w for all x at y equal to plus and minus of 1 is equal to 0. That's my original condition. I can then write this as w1 of x, okay, plus w2 of x at y equal to plus and minus of 1 to be equal to 0, okay, And then I can then write as W2 for all x at y equal to plus and minus of 1 is going to be equal to W1 of x. That's minus W1 of x. Okay. That's my modified boundary condition for W2. And again, if you ask me how is this, I mean, if you ask me the validity, just add these boundary, I mean, just bring it here, you just get the original boundary condition, which is this. Similarly, this is just the original boundary condition because I know that W1 is just a function of x only. Okay. So maybe this condition I will write it as 5b. Which that means that if you want to, solve for W2 and apply this boundary condition, you should a priori know the solution for W1. Okay. And this is possible, right? Because W1 is independent of W2. You can independently solve this ODE to get the solution for W1. Okay. But before that, in order to derive solution for W1 and then the solution for W2, I'll stop here for a couple of minutes. And I believe you are with me with this trick of solving how we basically solve a Poisson equation. Okay. So the entire trick basically hinges on this form that I'm assuming W of x and y as some form which takes care of just the non-homogeneous part, and I dump that non-homogeneous part into one independent variable only, and then the other contributions is dumped into a separate solution which is a function of the two independent variables. Okay. So that's the idea basically. And we saw that in order to evaluate W2, I must know W1 because this appears as a boundary condition in one of the faces. So for that, what I need to do is I need to separately solve for W1. Okay. So that's it. Then let's solve for W1. Okay. Solve for W1. So I know that W1 satisfies d2 W1 by dx2 equal to -1. And if I integrate this once, I have d of W1 by dx is equal to minus x plus c1. And if I integrate it once again, I have W1, which is just a function of x, as minus x squared by 2 plus c1x plus c2. Okay, that's it. That's the solution for W1. Maybe I'll write it as 6. Okay, and I know that if I now, so I need to evaluate these constants c1 and c2 for which I'll use the boundary condition. So what I will say is that W1 at x equal to plus and minus of 1 is equal to 0, which means I have minus half plus c1 plus c2 equal to 0, and then I have c1 plus c2 equal to half. And if I use the other one, that is at x equal to -1, I have what? I have minus half minus c1 plus c2 equal to 0, which means I have c1 minus c2 is going to be okay. Or maybe I should write it as c2 minus c1 is going to be equal to half. Okay. It's fine. It is fine. Okay, that's it. Then I just required, all I need is I just required to evaluate I just need to evaluate C1 and C2, for which what I'll do is if I just add, so from these two equations, if I just add it, I'll get what? I'll get 2C2. If I just add these two, I'll get 2C2 equal to 1, which means my C2 is equal to half. And if C2 is equal to half, I'll just substitute it here, from which I'll get C1 to be equal to 0. Okay, so that's it. C2 is equal to half and C1 is equal to 0, which means the solution for W1 of x is going to be equal to minus x squared by 2 plus half, which is going, so if you take a half common, you'll get 1 minus x squared. And that's obvious, right? Because you know that W1 satisfies the ODE, which is satisfied when you have the case of a plane parabolic flow. Okay, and that's a parabolic solution that you are getting here in the case where you have the walls as channels basically. Okay, so that's it. That's W1, right? So that's W1 basically. So now I know that all I need to know is, so since I know W1, I know these boundary conditions. These boundary conditions now become known to us, and I just need to solve for W2. That's it. So now the solution for W2, and I know that W2 just satisfies the Laplace equation, which is del square W2 equal to 0, and this is going to be del square W2 by del X2 plus del square W2 by del Y2 to be equal to 0. Okay, and subject to what? So it's subject to the fact that so these are the boundary conditions. So W2 at x equal to plus minus 1 of all y equal to 0. Okay, 2 at x equal to plus and minus 1 for all y is equal to 0. Okay, and the second thing is W2 for all x at y equal to plus and minus of 1 is equal to minus of W1, and I know that W1 is equal to this, which means this is just going to be equal to half of x squared minus 1. Okay, so these are the two boundary conditions. So this is my equation. Okay, maybe I should name this is 7, this is 8, and these are the boundary conditions 8a and 8b. All right, that's it. So the next step for us is to solve for W2, which basically satisfies this equation, which is the Laplace equation, subject to these four boundary conditions typically. Okay, that's our next task that we need to do. And for that, as we all know, the most common trick that we'll do is to assume. So what we'll do is we'll assume W2, which is a function of x and y, as some function of x times some function of just y, and this form, and the form of solutions that you take in this manner is known as, so the method is known as basically the method of separation of variable. Okay, that's it. All right, so okay, that's it then. Let's then try to substitute this form into this ODE. So what I'll do is I'll substitute 9 in 8. Okay, so I'll substitute this equation 9 in equation 8, and when I do that, so what should I get? So I'll get y times x double prime plus x times y double prime is equal to 0, where x double prime is just d2x by dx2. That's all that I'm writing, and similarly goes for y double prime. And then I'll divide this equation by xy, from which I'll get x double prime by x plus y double prime by y is equal to 0. And then I will write this as x double prime by x to be equal to minus of y double prime by y. And now here comes the important step, because we know that this is just a function of x. This is just a function of x. And this is just, a function of y. So the only possible way that a function of x can be a function of y is that it has to be equal to some constant. Okay, and in this problem we will take this separation constant as lambda squared, where lambda is a positive. If you take lambda squared, lambda just belongs to, so lambda is an integer basically. That's something that you can say. For instance, lambda can be equal to plus and minus of 1, lambda can be equal to plus and minus of 2, and so on and so long and so forth up to plus and minus of infinity. Lambda cannot be equal to 0, because that we'll see why lambda cannot be equal to 0 very shortly. Okay, now you can ask me that why didn't I take this separation I didn't take this separation constant as minus lambda square. That I will tell. So I'll give you the hint why I didn't take this as minus lambda square and instead I took this as lambda square. So hint is, and I will let you guys to think about this, because this concept had been explained in the lecture series, and I'll just give you the hint why this is the case. I'll ask you guys to think about it and try to find out a solution why I took this as lambda squared and not minus lambda squared. See, the reason is, along y, the boundary condition says that, see, along y, where are my boundary conditions? Okay, these are, so I know that along y, I have homogeneous boundary conditions basically. So I know that if I look into my domain, I know that when I move along y, I know that my velocity field here and here is going to be equal to 0. Which means that whatever solution I try to write down here, I know that they has to be equal to homogeneous, or they basically should go to 0 at y equal to 1 or maybe minus 1, and at or yeah, at y equal to 1 and at y equal to minus 1. Okay, that's that's the reason why I have chosen, my that's the reason why I have chosen the separation constant as lambda squared, basically. Okay, that means that whatever be, the solution of y, whatever be the solution of y, it should be such that it has to be 0 here and it has to be 0 here. So since I have two homogeneous boundary conditions along y, I will try my solution to be in such a way, okay, that I'll try to find functions of my solution in such a way that it will give me homogeneous, boundary conditions at the boundaries, basically. That's the reason why I have chosen my separation constant as lambda square and as minus lambda square. You can choose it as minus lambda square, and then when you solve, you will see that solution is not possible, which means that the only way you can have is that you choose the separation constant as lambda square. Okay. All right. I hope this is clear. Okay, that's it. Now then let's solve for x and y. So what we'll do is we'll solve, let's first solve for y of y. Okay, so y of y satisfies what? So it is y double prime plus lambda squared y is equal to 0. And since this is just an ODE, I know that the solution is just going to be of the form some, let's say, a times cos lambda y plus b times sine lambda y. Okay, that's precisely is going to be my solution, and subject to what? Subject to the fact that, so I know that w2, okay, at x equal to plus and minus of 1. I think I switched the sign of x and y actually. Let's check the boundary conditions once again. Okay, so hold on. Let's check the boundary conditions once again. X. Yeah, okay. So I think while explaining, I just switched the y's and x. So basically what I want is, I know that at x equals, so okay, maybe I just switched this y and x axis. That's typically what I did. So what I'm saying that at x equal to 1, which is, so my x axis is this, right? So x equal to 1 is this, and x equal to 1, x equal to minus 1 is this. So I know that x equal to 1 and minus 1, my solutions are going to be homogeneous, meaning that my velocity here and my velocity here, so w2 at this phase equal to 0 and w2 at this phase equal to 0. So I'm seeking homogeneous solution in the x direction, basically, not in the y direction. I'm very sorry for that. I just flipped the sign of x and y. So I'm seeking, so again I say the reason for choosing lambda, the separation constant, as just lambda squared is that I know that my w2 at this phase is going to be equal to 0 and my w2 at this phase is equal to 0, which means that when I actually calculate the solution of w2 along this phase, okay, I know that my solution is going to be homogeneous along that particular direction. Okay, I think that's that's the thing that I need to check. Anyway, I'll just check this once again before actually writing this. So hold on, let's see if I just, so this is right. Just some function. Okay, I think I wrote the solution wrongly. This is x equal to 1, which means that, okay. I think I choose the separation constants. So so the separation constant that I choose, this actually has to be equal to minus lambda square. Anyway, what I will do is I will try to explain this in a more clear version in the next week. Actually, so as I said, I just messed up little bit with the choice of this minus lambda square along x and along y. But the idea is that in whichever direction I have the homogeneous boundary condition, I I basically choose the sign of the separation constant basically depends on that. Okay, and this is something that I will try to clarify in the next week. So maybe what I'll do is I will not solve this now. Actually, I don't have that in my notes as of yet. So what I'll do is I'll stop here maybe on this form. Maybe I'll name this as equation 10. I'll stop here at equation 10. This choice, whether it will be minus lambda square and lambda square. So what we'll do is in the next class we'll try to go ahead with minus lambda square, and we'll try to go ahead with plus lambda square as well. Okay, and then we will see that either of the other. So one of the conditions, that if you choose the separation constant as minus lambda square, and if you choose separation constant as lambda square, one is possible while the other one doesn't satisfy the boundary condition. That's the in principle. Okay, that's the principle basically. So what we'll do is in the next class, so we'll choose. Okay, so maybe what we'll do is, so in the next class we'll take a case one, when the separation constant is minus lambda square, and we'll also take a case two when the separation constant is lambda square. Okay, and we'll see that either of these two is only possible, okay, because of the given boundary condition that we have. Okay, and we'll try to work out these two cases individually, and then things will be much more clearer. Okay, I apologize for the confusion that I have created at the end. uh, that is the choice of whether this sign is going to be plus and minus. I will so I'll clarify this in the next week, and then we will go ahead with the two individual choices. So these are the two choices that I have, right? I can either choose. See, actually I have three choices. I can choose this to be 0, I can choose that to be minus, and I can choose that to be plus. 0 0 is not possible, as we will see very shortly, because because choosing 0 will give you, a trivial solution. And then we'll see that either one of these two is not possible because of the nature of boundary condition that we have. Okay, because of the choice of w1x actually will dictate whether we'll choose a minus here or a plus in the coefficients of lambda square. Okay, this I will clarify in the next class. I'm sorry for the little bit confusion that has been created in the end. I'll try to clarify this in the next class. Okay. uh, all right, so I'm sorry. Okay, so in the next class onwards, in the next class precisely, we'll start from this step. Okay, uh, into calculating W2, and these things I'll clarify at that point. Okay, thank you for attending. Please, if there are any doubts, let us know in the discussion forum, and we'll be happy to address those doubts. Thank you very much.